So, is it true that you haven't sent me your homework, or it's me didn't get it?
Oh, because silly. I sent it to Professor Sosinski. I was actually going to ask you. Well, what if? Okay. I'm sorry. I forget to send it to you. Okay. Yeah.
Well, you mean he sent me your previous one? Previous one. It's from just. I guess it was in March. So I mean, I guess you. Well, I have the email from you with homework. Well, I guess it's homework 6 with some random complex as a first problem. Okay, so I guess it is time to start. So, well, I will send the results of the homeworks that I have. I guess on the weekend. So now I want to kind of discuss the last problem from the previous classwork, namely problem 5, this one. Okay, so if you have not the copy of, well, this file, please read it, because I want to kind of change to some kind of Blackboard. Okay, so what we have CW complex X. We know that it is simply connected by 1 of X 0 is 0, and we know that HK, okay, so we know that its dimension is equal to n, and we know that its homology is 0 if k is not 0 or n. So now we want to prove that in this case X is homotopy equivalent to the wedge of spheres. Okay, so we have discussed this problem last time, but still I want to repeat the arguments which we have here. So how to prove this homotopy equivalence?
So I think we always know that maybe finite dimensional, maybe just any CW complex is oh, never mind. Wait a second, sorry.
Okay, what do we know about this? Well, I mean, okay, so the question is purely, looks purely like, I mean, it's problem from the homotopy theory, okay? But the homology does not, does not work so well with homotopies. But so now we want to pass from some information about homology groups to some information about homotopy groups of X.
So yeah, because of we can use the Hurevich theorem. So we know that pi n is the first non-zero one, and it's isomorphic to Hn.
Yeah. Okay. So, well, I know. Can you write something, or it's better to me to write down some information that you have told?
Yeah, just a second. So we have these like plus Hurevich. And and 5K. That should be
Yeah. Okay. So, yeah. So now we want to pass from this information to, well, this corollary. Okay. So how we can do it?
I think we have a really general statement that for like any maybe it has to be sort of nice, like Hausdorff, weak Hausdorff compactly generated, but like most X, there's some map from a wedge of spheres where this is like some collection of, might be a really large collection of spheres, but it's this giant wedge of Sn alphas for a bunch of alphas that is it's a surjection on homotopy groups. Or whoops, not just X. So then once we know that, which I don't think is so hard. Uh-oh.
Oops, sorry. What? Sorry, I'm sorry.
So once we know that, then we know that all of the spheres in the ambiguous in W have to be n spheres. Oh, maybe not.
Well, actually, you don't know
Because-
the higher homotopy groups of X. Or probably, or maybe I haven't understood the thing you want to say. So actually, the statement we want to prove is the following. So claim is the following. So suppose X is CW complex, and we know, well, I want to be Y. So suppose Y is CW complex, and suppose its homotopy groups is 0 if K is less or equal than M. Then I claim that Y is homotopy equivalent to a CW complex with no cells in dimensions less or equal than M. Okay. Well, I mean with exactly 1 0 cell and no cells of dimensions 1, 2, etc. and M. Okay. So is claim clear?
Yeah.
So how to prove this one? Any ideas?
So we have the relation on the K skeleton that like phi K of Y is isomorphic to phi K of its K plus 1 skeleton.
Yeah. This is just the Celler approximation theorem, I guess.
Yeah.
So because any k, yeah, of course. So you have any map from k sphere to y is homotopic to one that lies in k skeleton, but the homotopy between, so any homotopy between such two maps is, lies in k+1 skeleton. Okay. So what do we know from the Celler approximation theorem? Okay, I probably I should remind. So if you have
Oh, just the statement of it?
yeah. So
Yeah. Is that if x and y are cell complexes and we have a map between them, then F is homotopic to some G that's cellular. Okay.
yeah, okay. So now I want to apply the theorem to the SK and Y. So any such map is homotopic to cellular. This means that the image of SK lies inside YK. Okay.
Yeah.
So, but now any homotopy of such map lies inside YK+1. So therefore, any, well, this means that pi k of y is isomorphic. Well, so this means exactly this isomorphism. Okay, but how do you want to apply this to the claim?
So because of it, we know that any map into the lower skeletons of Y, any map out of a sphere is no homotopic.
Yeah. So probably we should start from the case that we have discussed kind of in the previous seminars. So okay, so suppose we have a path connected CW complex. I want to prove that it is homotopy equivalent to the one with exactly 1 0 cell. So how can I construct such homotopy equivalence?
So we know that whenever we have a space X and it has a contractible subcomplex, then X is homotopy equivalent to the quotient. So we can just quotient out by, we can take the paths to be in the one skeleton and then quotient out by the paths connecting vertices to be in the one skeleton and then quotient out by those over and over again until there's only 1 0 cell.
Well, can you say it again, please? So what do you do? So
So you have 2 points inside the 0 skeleton.
okay.
And X is path connected, so there's some path in X. I guess by cellular approximation, we can take it to be inside X1.
Okay.
And then the image of this path should be, I guess it should be a contractible subcomplex of X, whatever image of P. Oops.
Well, I guess it is not true. So suppose X is a circle. So I mean, if you take any path, it won't work. So suppose I have a circle with the following cellular structure, CW structure. So I have 2 vertices and 2 edges. Okay. So now I want to take the path to be kind of this map. So okay, so image is a whole circle. And it is not contractible subspace of S1. So is it clear what the problem is?
Yeah. I don't know. Can we just do just X over its one skeleton instead?
Well, okay. Unfortunately, we can't.
Never mind.
Because so what do you know about one skeleton of any CW complex?
I'm not sure what you're getting at. I mean, if it's finite, then it's compact, I think.
No, I mean that one skeleton of any CW complex is just a graph.
Oh, yeah, yeah.
So okay, so if you have any graph, then you have its maximal tree.
Yeah, you can take its spanning tree.
So, and it's, how do you say spanning tree?
Yeah, yeah.
So its spanning tree is contractible by the very definition.
Yeah.
So you have, so and in the case of, well, in this case, its spanning tree is just one edge. Namely this one. Or for example, this one or another one, but still it is indeed contractible. Okay, so the problem with this one, I mean with X over its one skeleton, is the following. So, well, I don't claim that that any path-connected CW complex is homotopy equivalent to the one without with no well, with 1 0 cell and no 1 cells. For example, S1 is CW complex with, well, it is homotopy equivalent to the one with exactly 1 0 cell, but it's not homotopy equivalent to this to the one with no 1 cells. Well, no, I mean, well, I guess it is obvious. So, okay, so
yeah.
Okay, so now we want to pass from kind of in this statement from m equal to 0 to m equal to something, for example, to 1. Okay, so suppose we have simply connected CW complex. I want to prove that it is homotopy equivalent to the one with no 1 cells and exactly 1 0 cell. Okay.
Okay.
So we know that we already know that we can suppose that Y has exactly 1 0 cell. Okay, so in this case, what is its one skeleton?
It's has to be a wedge sum of S1s, I guess.
Yeah, of course. So okay, so claim in the case m equal to 1. So we know that Y is homotopy equivalent to well, CW complex with 1 0 cell. So therefore, okay, so therefore its first skeleton is just wedge of circles. Okay. Okay, so now I want to prove that I can kind of contract them. So how I should do this? Yeah. So what do we know? So we know that P1 of Y is 0.
So I guess the identity maps of all of the S1 alphas into Y have to be null homotopic.
Yeah, okay. So we have this map and it is null homotopic. Okay. So what does mean that that this map is null homotopic?
Then I don't know if it's exactly the identity map, but it's like almost their identity map. And then if it's null homotopic and it's their identity map, then they have to be contractible.
Yeah, but so okay, so suppose we have okay, so let's start from the beginning. So what does mean that this map is not null homotopic? So this means that we have a map from the cone over this wedge. Okay. So in particular, since cone is just the quotient of the cylinder, we have a map from such a product. So we have the wedge sum cross unit interval to Y such that it is an identity on the wedge cross 0, and it is a map to the base point on wedge cross 1.
Yeah.
Okay. So okay, now I want to apply the Borsig theorem to this homotopy. Okay, so I have the following picture. I have so this wedge lies inside Y. So therefore, this product lies inside Y cross unit interval. And I have a map on the on the Y lies at the bottom, and the homotopy on its cellular subcomplex. Okay. So and now well, the Borsig theorem says that I can extend this homotopy to whole Y. But this homotopy is homotopy between identity map and the map that maps all whole one skeleton to the point. Okay. So please ask any questions that you have.
Yeah, I guess it's okay. And well, in the map that we define on the base on all of Y is just the identity.
Yeah.
Okay.
So
yeah.
We have Y for 0. This map is just, oops, this is just identity map. So therefore, I have the homotopy from Y to Y such that it kind of contracts its one skeleton. Okay?
Yeah, looks good.
So okay, so can we now prove the general statements? Actually, I claim that we can use the similar argumentation to the general case.
So inductively, we know that we can take Y to have no, have 1 0 cell and then no, like m-1, m-2 cells.
Yeah.
So its M skeleton has to be a wedge of M spheres.
Yes. So okay, I'll write it down. So okay, SKM of Y is just wedge of M spheres.
It really does feel almost exactly the same as this argument, but so I guess so we know that the pi m of Y is 0.
Yeah. So yeah, of course.
Conclusion is also no homotopic, and we can apply Borsig lemma again.
Okay. So yeah. Okay. So any questions about? Okay. So we have proved this claim. So if Y have well, if lower homotopy groups of Y is 0, then the corresponding skeleton is just a point. Okay, so now I want to prove this homotopy equivalence. So how can I prove it?
So I guess by our claim, we know that in like these two conditions, or I guess just this bottom one, we know that we can take it to have no smaller than n cells.
Okay.
And then it's n-dimensional, so the largest cells that it can have are n cells. So it has to be exactly like this wedge of n spheres.
Yeah, of course. So if we have only one 0 cells and only, well, okay, so if our CW complex consists only on 1 0 cell and some n cells, then it is just a wedge of spheres. Okay, so this is just because the bound, so how we can obtain the CW complex. Okay, so we have a maps from the boundary of our cells to the lower skeleton. But lower skeleton in our case is just a point. So we have the constant map from the boundary to a point. Okay, and in this case, we obtain all that we can obtain is just a wedge of spheres. Okay, so is it clear?
Yeah, I think so.
Okay, so I guess that's all on this problem, but I have well, one great result that I want to discuss right now. So, namely, the result is called the Whyphy Theorem. So, I guess you haven't discussed this on your lectures. So this well, the claim is the following. So suppose we have a map from y to x such that it induces isomorphisms on homotopy groups. Then F is homotopy equivalence. Okay, so have you discussed this theorem on the lectures?
This week's lecture is still not online, so I have not watched it, so I'm not sure. But not any previous weeks. We haven't discussed it.
Okay, so I guess this week's lecture was about singular homology. So it wasn't well mentioned. Okay, so I want so I claim that well, I mean this is very strong result. So okay, for example, from this theorem, you can easily prove that infinite dimensional sphere is contractible, because you know that its homotopy groups is 0 because, well, just because of Celler approximation theory. And you have a map from a point to well, okay, so you have a constant map from infinity sphere to a point, and it induces isomorphisms. So therefore, it is a homotopy equivalence. Okay.
I have a question about your statement.
Yeah.
You mean F star is a map from pi star of y to pi star of x?
Yes.
And that's all? But F is always such a map.
Oh, sorry. I mean such that this map is isomorphism.
Okay, thank you.
Sorry. Yeah. Okay, thank you. So okay, is the statement clear?
Yeah, and it has to be like a map has to induce it. It isn't just saying that if two spaces homotopy groups are the same for all k, then
No, it isn't true. So we will discuss examples. Well, but now we'll discuss an example in which we have the spaces with the same homotopy groups but not homotopy equivalent. But now I want to prove this theorem. Okay. How we can do this? So actually, Whyphy theorem says that we have, well, if and only if, but another direction is clear. So if you have the if F is homotopy equivalence, it induces isomorphisms on homotopy groups. Okay. So now we want to prove the theorem to another direction. So suppose we have a map that induces isomorphisms on the homotopy groups, and we want to prove that it is a homotopy equivalence. So we can reduce these to the following statement. So suppose we have we can we can take X to be a cylinder of this map, and F to be the canonical embedding. Okay, and in this case, we have we can assume that Y is a whoops, sorry, I haven't write it down, but of course X and Y is are CW complexes. Well, taking X to be the cylinder of this map, we can assume that Y is a subcomplex of X. Therefore, we have the following modification. So we have the long exact sequence of homotopy groups, and it implies that we have pi star of xy is 0. Okay.
Mm-hmm.
So, and I want to well, the claim is that if we have such a pair, then X is homotopy equivalent to Y. Namely, no, I mean, we in this case we have the a deformation retraction from X to Y. Okay. So is my modification clear, or?
What is pi star of x and y?
Sorry?
What is pi star of x, y?
Well, it is relative homotopy groups. Or probably I should remind. So this is just, well, do you remember what the relative homotopy groups are? So this is just the set of homotopy classes of maps from such pair to X, Y. And my homotopy preserves my homotopy preserves this relation. This means that all homotopy should map the cylinder over boundary sphere to Y. Well, this is only assumption. Okay, so is it clear? Or
yes, thank you.
Okay. So how to prove that in this case we have X homotopy equivalent to Y? So actually, I claim that I can that we can construct a homotopy such. Well, I have Y is a subspace. Well, I claim that we can construct a homotopy. Well, homotopy equivalence that maps any cell of X that is not inside Y to Y. Okay. So let us argue by induction on well on some dimension. So I have X, Y, and suppose I have already constructed kind of homotopy between identity of X and a map G from X to X such that well, G of X K minus 1 lies inside Y. Okay, and my homotopy is relative. This means that my homotopy is identity on Y. Okay.
Yeah.
Okay, so now I can take any K cell, well, of X without Y. Okay, so such well, such cell is just a map from dk boundary dk to X and xk minus 1. Okay.
Yeah. So then we can use our homotopy to send the boundary of the cell into Y, and then by the left, because
So can you say it again, please?
yeah, using our homotopy, because yeah, using our homotopy, we can send the cell's boundary into Y.
Yeah. So we have the composition to X Y. Okay.
And then by our work on the left, we know that it has to be no homotopy.
Yeah. So we know that G composition with phi from dk boundary dk to X Y is null homo. Sorry. Homo topic. Okay, so and what does it mean? Actually, this means that, well, what does mean that relative, that element of a relative homotopy group is 0?
Wait, sorry? I thought we knew that this map was no homotopic because we already knew that.
Yeah, okay, yes, of course we know that we know this, but I'm asking what does it mean? So what does mean that this map is null homotopic? I mean, in the relative case, it is not well, null homotopic does not mean that it maps well, that this map is homotopy to one to the constant one.
Oh, it's homotopy to the base point of that mapping space, which is the map into Y.
Yeah, it means that.
Y.
Yeah. So null homotopic means that it is homotopic to map. Well, to map. Well, to some map that maps dk to y. Okay.
Yeah, I think that makes sense.
Okay, so actually, it is we are almost done. So, what we can do now?
So Phil, that helps us extend our homotopy like up a dimension.
Yeah. So actually, this means that attaching k cells to x is homotopic to attaching well to attaching k cells to y. Okay. I mean that there is a homotopy equivalence between sorry, I mean there is a homotopy equivalence between the canonical map from xk minus 1 with this k cell to x and a map to y. Okay.
Yeah, where the homotopy on the k minus 1 skeleton is like by assumption, and then this one is the is the other. No, okay.
So now we can apply we can apply this kind of homotopy to whole k cells, to all k cells. Okay, and then we can use the Borsig theorem to extend our homotopy to x. Okay.
Yeah, that's nice. Yeah.
So and now we can use kind of induction on dimension because, well, we have some kind of infinite homotopy, but it is constant on well, it is constant on each skeleton from some t. Okay. And this implies that x is homotopy equivalent to y.
Because inductively we like have a strong deformation retract.
Yeah, yeah.
Okay. Okay.
Okay, so I guess now we can discuss some kind of counterexample to Whyphy theorem, and stop there. So I guess we can discuss the material of the yesterday's lecture on the next week, because I guess it is not online yet. Okay. So is it okay for everybody, or?
Yeah, sure.
Who and what?
Yeah, it's okay. And may I ask about homework? Do we have homework this week?
Yeah, I guess you can. Well, I guess no. So you are homework free this week, and well.
Okay.
So I will send the results of your previous homeworks, and you can. I guess you can send the previous homeworks. The corrections with full credit if you want to. Okay, but before I should send you the results. So okay, so now I want to give an example. So the claim that I claim that it is not true that if x, that if pi star of x is isomorphic to pi star of y, then it is not true. Then x is homotopy equivalent to y. Okay, so I guess we have already discussed the example of two spaces that have the isomorphic homotopy groups. So okay, the first example is the first space is just two sphere. So do you know any example of a space with the same homotopy groups? Well, okay, we can start from the space with the same homotopy groups. Okay, so what is the difference between S2 and S3?
Pi 2 of S2 is non-zero. Pi 2 of
Okay,
S3
so well, but okay, so but what about others? Well, do you remember that pi k of S3 is isomorphic to pi k of S2? if k is greater or equal than 3.
Yeah, that's from the hop vibration and the long exact sequence.
Yeah, okay. So okay, we have such isomorphisms. So but still we know that pi2 of S2 is not 0. And do you know what is pi2 of S2?
Z.
Yeah, it's Z. So do you know any space with well, okay, so we can start from the kind of easier question. So do you know any space with exactly one non-trivial homotopy group?
Like CP infinity? Maybe?
Okay, so yeah, we have CP infinity. So how well, okay, so your claim is that CP infinity has only second homotopy group non-trivial, and any other is 0. Yes.
Yeah. Okay,
So
so it was a homework problem, right?
yeah, but okay, so how we can prove this? Prove it.
So do we have a fiber bundle like S1, S infinity, CP infinity? I think
Yeah.
and then looking at the long exact sequence, this disappears everywhere. So we end up, I can draw more if you want, but the idea is that this is going to disappear.
Yeah, we
because
have
it's contractible.
pk of CP infinity maps to pk minus 1 isomorphically to pk minus 1 of S1. Yeah, it is, I guess it is what you are saying. Yeah.
Yeah.
Okay, so therefore, yeah, so pk of CP infinity is Z if k is equal to 2 and 0 otherwise. Okay, so and now what is well, what is the second space?
Sorry?
So, well, we have started from this question. So I want to construct a space with the same homotopy groups like with I mean sorry with homotopy groups of S2 but not S2. So what is the second space?
So to have the same homotopy groups, can we use CP infinity times S3?
Yeah, so we can take just CP infinity. Well, this is just because the homotopy groups of the product is just sum of the homotopy groups. Okay.
Yeah.
So, but the question is why these two guys are not homotopy equivalent.
I guess I don't know the homology groups off the top of my head, but I think the ones for CP infinity are not as simple. The homology groups for CP infinity as compared to the homotopy, so they're probably going to differ in homology.
Yeah. Okay. So the idea is that they both have different homology groups. So okay, we know the homology groups of S2. Yeah. Well,
yeah, it's only non-zero for k equals 2 and 0. Or I guess, I don't know. We can look at it reduced if you want. I don't know if it matters. It probably doesn't matter.
well, okay. So the question is, okay. So let us start from the kind of easier question. So how to compute the homology groups of CP infinity? So actually, it is it is almost obvious. So do you know cellular structure of CP infinity? Or for example, we can start from CPN.
Yeah, it has an even, it has a 2k cell for 0 to n.
Yeah, and okay, so using this cellular structure, you can easily compute its cellular homology groups. Yeah, because your cellular chain complex is just Z maps to 0, maps to Z, maps to 0, maps to etc. Okay.
So it's just z in every even dimension, or maybe.
Yeah. So this is 2k, 2k minus 1, 2k minus 2, etc. So is it clear?
Yeah.
Okay, so now, the last question is the following. So how can we compute the homology of such a product? Well, actually, you can define the cellular structure on this product. Yeah. So as cells of this product, you can take just the product of cells.
Yeah. So now, maybe I guess I should have one cell in every dimension, or maybe a couple.
well, I guess, well, okay, so we can try to see what happens with the cells. So, okay, I have, so, okay, I'll start from, sorry, from 0. So this is 0. So I have Z maps to oops. So this is just my cell cell complex for CP infinity. Okay. Now when I take kind of product with S3, I have two kind of cells. So I have cell of CP infinity cross 0 cell of S3 and cell of CP infinity times free cell of S3. But still my boundary maps are zeros. So I have such two such complexes. So I have, sorry. So I have the following. So my, well, I claim that my, sorry, my cell complex of the product is the following direct sum of complexes. Okay. Okay, or there are questions.
What is the second chain?
Sorry?
What is the second chain?
You mean this one, yeah?
Yes.
So this this complex is just CP infinity cross 0 cell of S3. And this one is cellular chain complex for CP infinity. Oops, sorry. Cross free cell of S3.
Yeah.
So it starts from in the dimension 3 and well, and it looks like the chain complex of CP infinity just shifted well, with shifted dimension. Okay. So, and my cellular complex looks like just direct sum, and from this I can easily compute the homology. Namely, it has well, namely H star of CP infinity crosses 3 is Z. Well, okay. I mean, I can write. Well, it is 0 in dimension 1 and Z otherwise. Okay. Okay, so if you have any questions, please ask them, and if not, I guess that's all that I wanted to discuss for today.
Okay.
Okay, so okay. So thank you for coming. Goodbye.